Cambridge International AS and A-Level Physics Coursebook by David Sang et al. Chapter 29, Quantum Physics. End of chapter questions. Number 1. Calculate the energy of the photon, frequency of this. All you have to do is just to write your equation. E is equals to h times f. H is constant, the frequency is given. We can calculate that one. Our answer here is 2.7 times 10 to minus 15 joule. So I'll write here the constant. Our constant is h. The Planck's constant is 6.63 times 10 to minus 34 joules times second. Number 2. The microwave region of electromagnetic spectrum is considered to have a wavelengths from 5 mm to 50 mm. Calculate the range of microwave photons. So here we have your lambda 1 and this is your lambda 2. So we need to calculate two frequencies here. Let's start with F1. So in terms of frequency 1, we have lambda, velocity over lambda 1. So that is just 3 times 10 raised to 8 meter per second divided by lambda 1. That's 5 times 10 to minus 3. So our frequency here is 6 times 10 to the power of 10 hertz. This is your frequency. Now you can calculate now your energy. So this is your E1. Energy 1 is equals to HF1. So by using that, we can have around 4 times 10 to minus 23 joule. Let's go to F2. F2 using lambda 2 will be velocity of our lambda 2. Okay, so that's just 3 times 10 raised to 8 divided by lambda 2 is 50 times 10 to minus 2, it is centi. It will give us around 6 times 10 raised to 8 hertz. It's a bit lower frequency. So we can calculate your E2. E2 will be HF2. The answer will be around 4 times 10 to minus 25. There you go. You have range of energies. So you have two energies here, this one and this one. Let's go to number 3. In a microwave oven, photons of energy are used to heat the food. Calculate in joules. So just multiply by the E. So you're going to write here 1.02 times 10 to minus 5. Okay. Okay, we just multiply it by the charge of the electron. We know 1.6 times 10 to minus 19. That's right. Then we have the answer 1.63 times 10 to minus 24 joule. Calculate the frequency of the photon. Formula, energy equals to h times f. So therefore, your formula of frequency is equals to energy divided by the Planck's constant h. We know it's at the top. The energy is calculated, this one. That is your energy. So calculating your F, it's around 2.46 times 10 raised to 9 hertz. That's right. This is now your answer for the frequency. Let's go to the third one. Calculate the wavelength of the photon. And so wavelength is simply lambda is equals to velocity all over frequency. There you go. Then, you know, this is the speed of light, 3 times 10 raised to 8. Okay, all over your frequency here. Your frequency is actually this one. Yeah. Then calculating that, it will give us around 0.12 meters. This is the answer. Let's go to number 4. Alright, let's have number 4. An alpha particles of 5 milli are emitted in radioactive decay of radium. Express this in joules, so let's have letter A. So it's just 5,000, 5 mega, so it's 5 million. Okay, multiplied by the electron volt, 1.6 times 10 to minus 19 coulombs. So I don't need to put units because Cambridge exam will give you the units. So this is around 8.0 times 10 to minus 13 joule. Okay, let's go to B. Electrons in cathode ray tube accelerated through a potential difference of 10,000 10 kilovolts or 10,000 state in electron in terms of joules and electron volt. So let's go to B. In terms of joule is I think the best. Yeah, so energy is equals to Q, the charge of electron, and the voltage is given. So this is 1.6 times 10 to minus 19, all right, times the voltage is given 10,000. Okay, then we can have around 1.6 times 10 raised to negative 15 J. So this is now your answer. In terms of electron volt, so in EV, okay, just divided by, actually it must be 10,000 also. So it actually just divided by 1.6 times 10 to the minus 15, just divided by E, the charge of electron. Now, of course, it will go back to 10,000, okay, electron volt. Now let's go to C. In a nuclear reactor, neutrons are slowed, energies express this in EV. So you have 6 times 10 raised to minus 21 divided by E. Just divided by the charge of the electron. And it will give us around 3.8 times 10 to minus 2 electron volt. That's the answer for C. Let's go to number 5. It's not difficult. Number 5. A helium has a charge. You have given the charge Q, you have your mass, and you have your volts. Calculate its kinetic energy in electron volt. So, calculate its kinetic energy. Let's start with letter A here. So, for letter A, work is equals to QV. Okay? Now, that work is actually your kinetic energy, which is equals to Q times the V. Then, the charge is given here. At the top, this is your charge. And the voltage is also given here. So, you can calculate that one. Then it will give us around 2.4 times 10 to minus 15 joule. Finished? Let's go to in electron volts. So by the way, this is B. Sorry, this is the answer for B. Okay. The answer for A will be that number 2.4 times 10 to minus 15. We just divide it by E. So you can have electron volt. So for letter B, it will be around it will be around 15,000 electron volt. So this is now your A answer. What about C? What about the speed? Okay, the speed will be here. We have calculated the kinetic energy. Kinetic energy equals to mv squared over 2. Alright, so it means to say that from this formula we can have velocity is twice the square root of twice the kinetic energy all over the mass. Okay, kinetic energy is calculated. Okay, this is calculated already, this number here, right? And the mass is also calculated here. It's been not calculated but given here, that. So everything is given. You can calculate your velocity. So your velocity is around 8.4 times 10 to the 5th power meter per second. Let's go to number 6. Simple. Yeah. Let's go to number 6. Ultraviolet light of photon energy. So this is your E. This is your E. Is shown onto a zinc plate. The work function, this is your phi. So this is your phi and this is your E. Alright. Now, I forgot to write here what is asked here. Okay. What is asked here is the kinetic energy. Kinetic energy, what is asked? Okay, I just write it here. What is asked here is the Ka max. Okay. In J and electron volt. Okay, there are two. So let's start. The formula is simply energy from Einstein is work function plus kinetic energy maximum. So it means to say that our kinetic energy max would be energy minus the work function, right? So let's continue at the top. So your energy is given is 2.5 times 10 raised to minus 18, all right? Minus, so your work function is 4.3, okay? You are going to multiply it by 1.6 because it's electron volt to negative 19. So it will give us our Ke max Okay, it will give us 1.8 times 10 raised to negative 18 joule. That is your K max. There you go. Now in terms of electron volt, okay, in terms of EV, okay, it will become 1.18 times 10 to minus 18 divided by E. Okay, divided by E, it will give us around 11.3 electron volt. There you go. That's your answer. Let's go to number 7. Number 7, calculate the minimum frequency, okay, that will cause the emission of photoelectrons from the surface of gold. So your function is here. Now we just use the formula. Work function is equals to HFO. FO means the minimum frequency or threshold frequency. So now by just using the equation, you have F sub O, minimum frequency or threshold frequency, work function divided by the H. The work function is given, it's 4.9 multiplied by the electron. Charge of electron, you can put it, the H, the Planck's constant is also given. It's a constant, so you can calculate that. It's 1.2 times 10 to 15 hertz. There you go. That's your answer for number 7. Let's go to the last one. Let's have number 8. Okay, let's have number 8. Okay, let's adjust it here. All right. There you go. Number 8. Okay. Figure 29.25 shows the energy levels in the helium ion. Okay. Calculate the energy in joules that's required to completely remove origin in its ground state from the helium nucleus. So whatever is the ground state energy, we will also use the same amount of energy to completely remove, yeah, from the nucleus. So our answer for A will be here. So energy that will be required will be equal to the ground state. Okay, ground state is N1. So we know energy is equals to what? 54.4. We multiplied by the charge of electron. So E will be around 8.7 times 10 to negative 18 J. Alright, so that is our letter A. Let's go to B. Calculate the frequency of the radiation which is emitted when the electrons drops from N3 to N2. State the region of the electromagnet in which this radiation lies. Again, we need to remember our R, me, remember Vox G, the electromagnetic spectrum. Okay, so from N3 to N2. So technically it's from this. So this is your initial, and this is your final here. Okay, so let's go to B. So the change in energy is from where? Final, it's 13, negative 13.6 electron volt, okay, minus the negative 6.1 electron volt also. It will give us around 7.5 electron volt. That's right. Then we can calculate now we can calculate our F. Let's go to energy first. So your energy here, your change in energy here is equal to 7.5 times E, the charge of electron. It will give you around 1.2 times 10 to minus 18 J. All right. Now let's go to the F now, because we need the frequency actually. So F is equals to the change in energy over the constant H. So it gives us around 1.8 times 10 to the 15 hertz. Now that's our answer for letter B. Let's go to C. For letter C, let me have maybe the answer in this area here. Okay, okay. Without further calculation, describe qualitatively how the frequency of radiation emitted when electron drops from N2 to N1 compares with the what? with the drops from N3 to N2. So the other one is N2 to N1. So now we can actually explain here. You can say that is letter C. Okay, the drop in energy, okay, from where? From N2 to N1, you can see that is greater compared with N3 to N2. So what does it mean? So F now, F is much higher. Okay? So from N2 to N1, your F is much higher. Reason for that, as F is directly proportional to energy. Remember that energy is H times F. Don't forget to subscribe our channel. Thank you.